Right, I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. This time we have just to talk about your creation, math, and just thank you, Lord, for your many blessings to us, Lord. In your name we pray. Amen. So you had a question, like basically your question is more or less, what's the deal with the Dirac Delta function? And paraphrasing. So let me just tell you a little bit about the Dirac Delta function and its uses. So usually I would say the first thing I would talk about is the idea of something like the notion of like hitting a spring with a hammer or something, or maybe you got a spring, right, and a mass, right, and then you've got some hammer, and you hit it, right, and all right, so, and of course this is sliding along some. I mean, you can give it friction if you want, whatever, but you can sad picture. But you imagine just hitting a spring with a hammer, right? Now, so how would you want to describe that? Like, how would you want to model that? I mean, if you just think about the physical process of hitting a hammer on something, you can't. It's not very practical to try to measure exactly the time application of the force, right? Like, that's pretty hard to figure out. I think one of the only things you really have much hope of measuring is the change in momentum, right? What's the impulse that's delivered by the hammer to the mass, right? Because you can look before and after, and you can see the change in momentum. That would be the impulse, right? But what's impulse? You know, dp dt.
Change in momentum
is equal to the force, right? So yeah, so like change of momentum exactly dp is f dt. Now, if you think about the force, it's something like, you know, at the moment that you hit the thing, right? What's the force look like? It's, you know, the process of hitting a hammer, it's 0, right? And then it's just this big old, basically, spike, right? And so the actual force time thing could be something kind of, I don't know, it could be all kinds of wacky, you know, maybe the hammer bounces. A lot of complicated stuff could happen in the process of the hammer hitting the mass. But if you ignore the kind of complicated stuff, what you're really looking at is just some kind of like bland spike, right? What's the area under the spike? What's the interpretation of that area? So basically the integral around any interval I, right, of f dt should be equal to the change in momentum. And it really, and you start idealizing this, right? You start idealizing it, and then you don't have a finite, you don't have this window of time, you've just got an instant. Right, so in the limit of that idealization, you get the Dirac Delta. It's just this spike, where in this particular context, the area of the spike has the interpretation of the momentum delivered to the mass. And so the formula for that, of course, is the force is like equal to the momentum delivered, whatever that is, let's say J naught, Dirac Delta, T minus T naught, right? Where, of course, the integral of J naught Dirac Delta function T minus T naught is just equal to dt, right? Is just equal to J naught. And that's basically for T naught plus minus epsilon, right? To T naught plus epsilon. For as small an epsilon as you like. Now, you guys haven't had real analysis yet, right? But if you had real analysis and you studied integrals carefully, this would be very vexing. It's an absurdity to say that you can have an integral which works out to a finite thing, and yet it's just an integral at a point. I mean, basically, you could take the limit as epsilon goes to 0. That should be 0, right? And yet it's not 0, it's always j naught. So something funny's going on here. I mean, it's not possible in terms of functions to have an integral. You can't have a function which is everywhere 0, except for one point, and yet somehow produces a finite integral. It's not a function. So, and yet, again, Dirac Delta function. So, the definition, as you saw, is just what? It's like something, like you said, it's kind of implicit.
Yeah, phi of 0 is equal to the integral from negative infinity to infinity of Dirac of t, Dirac Delta of t, phi of t dt.
Ah, okay. Of course, you can make a substitution and say phi of t naught.
Yeah, you can do use substitution techniques kind of in a way to evaluate it.
And I think to say that, you probably need to know that, I don't have to put it's still phi of t.
I think, if it were another function of t, you wouldn't have to change it.
Yeah. So I like to say, my slogan for this is the Dirac Delta function changes integration into evaluation, right? Now, where does this fit into a larger story? Another place where you might, besides just, supposing you want to model a force which is just infinite at one point, and yet the area in the force time graph is bounded, right? Another place where you might might think of the Dirac Delta function is something like this. Another application where it comes up is switch, right? So suppose you got here's your time voltage graph, right? And your switch is, imagine the switch being, it could be voltage, it could be current, doesn't really matter, voltage or current, whatever floats your boat. But the switch is switch is open, right? So you got 0 current or 0 voltage, and then, well, I guess I should be talking about. Let me talk about current. So, making sense. I'll stick with current. So current. So the switch is open rather, right? So there's no current flowing, right? And then at time t naught, you close the switch, right? And then what happens at that instant?
The spike.
Right. You go from, it depends on what else is in the circuit, of course, but after you close the switch, then you got some finite current past that point, right? Fine, if you want to make it specific, we can suppose we have silly voltage source here and a resistor, here's your E, here's your R, then I is equal to E over R. We know this. Okay, there. Now I have to place Ohm's law. Right. For example. So what's the derivative of the current in this situation? See, because the current, right, is equal to, in my specific example, epsilon over R, and then the unit step function of t minus t naught. So what this is, it's 0, and then it's E over R, a constant, right? I'm not really committing to the value of the current being E over R at the time t naught. Actually, at time t naught, I don't really know what happens. It's kind of a mystery. Again, this is a simplistic model for the physical reality. Physical reality, although it's hard to appreciate in this world we live with these time-delayed LED lights and with these stupid fluorescent things. But back in the day, we had these things called incandescent bulbs, right? And as soon as you hit the switch, thing starts basically, it heats up really, really fast. You can't really, it's almost immediate, right? And generally speaking, there's something called bounce with switches, right?
Yeah, back when we goes over its set, level of current or whatever, and then returns back to it, right?
Right. I'm actually physically talking about bounce. When you close the switch, it actually, there's usually some kind of actual bounce in the switch, so that it's not a clean for real mechanical switches at least. I don't know how I'm not as well versed in electrical switches or anything, but
No, they still teach us that. I think in like 201 they taught us about balance for some reason.
but it's this is an idealization. This graph I drew of a switch, right? The truth is, it's more complicated. There's actually some kind of window of time where it continuously transitions from one to the other, and yet a mathematically useful idealization of it is that it's this unit step function. It's this discontinuous beast, and it's very reasonable to suppose then, whatever this means, that ddt of u of t minus t naught is equal to what? Now, I was asked this on a quiz in my junior level electricity and magnetism course, and I could not figure it out. At the same time, I was taking real analysis and being taught things like, if I say C, I pick C and I use transitivity of inequality, I lost points. I'm like, why did I lose points there? And then she said, because you didn't say that C was a real number. And I said, but I said C was a real number at the top of the page. We write math proofs top down, right? Yes, but you should be emphasized when you use transitivity of real numbers here. And then I'm asked, what's the derivative of the unit step function in the other class I'm taking? It's like, you go from this like unrealistically careful to the point of being meaningless math to, that kind of, it did not help me. I understand in retrospect what she was trying to do, but it was not productive for me. But anyway.
So is that where the Dirac Delta function comes in? Is it's kind of almost treated as an infinite change?
See what it is? It's zero, like it's this constant, right? And then what does it do?
It jumps.
It increases, right? Yeah, so it's positive infinity, right? It's essentially got a vertical tangent. But you realize I'm saying all kinds of mathematical heresies here. I'm talking about a tangent to a discontinuous function. We know functions are only differentiable if they're continuous. I'm telling you then the derivative of this discontinuous function is this Dirac Delta function. How can this be reasonable? Well, because this is not actually a function, it's actually a distribution. To understand it properly, you have to understand it as the limit of a sequence of functions. You might have talked about that in your other class, 10 functions.
What function?
10 functions.
Not yet.
It's not unique. You can use these guys. I'm not doing it right. And so forth. Like, you can build this family of triangular functions, area under each one of these being 1, and the limit as n goes to infinity of that is the Dirac Delta function in some meaningful sense. Dirac did this stuff before it was well-defined mathematics. After Dirac introduced the Dirac Delta functions, some pretty bright mathematicians came along and formalized it. And Schwartz, the one I think in the 20s.
Like the same as
I've
the
not
Schwartz
studied these
inequality.
things carefully. What's that?
Same as the Schwartz inequality.
I don't think so.
No.
I think that Schwartz is earlier. But I don't know, there's a lot of Schwartzes. I think one of them has and it's maybe spelled differently too. Oh well, maybe when I teach math history I'll sort this all out. So in other words, I'm not going to sort it out. But but anyway, this is, you're more or less asking for a little bit more intuition on it. Here's a little bit more intuition. You can think of it as entering, as soon as you start asking like differentiation in this realm, it comes up in some sense. If you want to meaningfully extend the derivative, but it comes at the cost of not working with functions anymore. There are any number of things you could ask me I couldn't tell you about here. You could ask me, is it a function if you extend to the really long line? Like if you throw in infinity, is it a function? I don't know. It'd be cool if it was. But it feels like since I don't remember that, it's probably not true. I would have seen that by now. But anyway. Alright, so guys, you do Dirac Delta, did you do Laplace transforms in diffie-q?
Oh yeah.
Yeah, so you guys know the deal. F of s is what?
Oh boy. Integral e to the s?
Oh, it's like, yeah.
Negative st or something?
Right.
Yeah, the function of t dt.
All right. So in other words, that's the Laplace transform of f at the frequency domain s, right? So what happens when you take the Laplace transform of the Dirac Delta function based at t naught?
I want to say 0, but
Integration turns into evaluation. So all you got to do is put t equal to t naught.
see, it's Is that it?
Yeah, that's it. I know, right?
It seemed like a trick question.
I know. So the Laplace transform, like what happens if you take, for example, f of t, u of t minus t naught, how does that go? So let me get straight to the point here. When you plug that over into here, it's 0 all the way up to t naught, right? So this becomes the integral from t naught to infinity of f of t e to the minus st dt. And then what you do is you make a substitution. Let's let u equal to t minus t naught. So t is equal to u plus t naught, among other things, right? And dt is equal to du, right? U of t naught is what? I gather you guys did not cover the discontinuous case when you studied Laplace transforms, correct?
Doesn't sound familiar.
Yeah.
That's unfortunate. That's the whole point.
We were given a chart.
The whole point of studying Laplace transforms is that it allows you to do discontinuous functions. Otherwise, I can solve all that stuff without Laplace transforms, right? But anyway, so with this change of variables, this is the integral from 0 to infinity, right? And f of t becomes f of what? F of t is equal to u plus t naught. And I have e to the minus s times u plus t naught. dt is du. And then you gotta tilt your head and squint a little bit here. This is e to the minus s t naught, the integral from 0 to infinity, f of u plus t naught, e to the minus su du. Using lots of exponents and the fact that that's a constant with respect to the integration. S is a fixed but arbitrary variable we're introducing, and t naught is a fixed time here. So what's this? That's the Laplace transform of f of u plus t naught at s. So this gives us this theorem, like the inverse Laplace transform of like e to the minus s st naught, e to the st naught rather, of, oh stink, I don't know, I'm trying to remember the right way to set this silly thing up to make it useful for us.
It's 5
Oh, be
o'clock
quiet.
PM.
I didn't ask you. Silly clock. All right, so let's see here if I can. I mean, this gives us a rule for how we. See here. In particular, if we take f equals to 1, right? Then we have the Laplace transform of the unit step function at t naught is just equal to what? What's the Laplace transform of 1? Do you remember?
It's E. I said so.
Excuse me, it's one over us. Sorry. This is not the one I want. There's a slick way of rewriting this that's useful that I need for our discussion to be best. Come on. I usually got the Laplace transform sheet sitting around everywhere. I will find it. Where's my...
Useful sheet on the final.
Here. See?
Useful sheet on the final.
So, close cousin to this is that the inverse Laplace transform of e to the, I usually use a instead of t naught, e to the minus as f of s, in the t domain, e is equal to f of t minus a, u of t minus a. Okay, so there's the inverse theorem, basically. Okay, I was trying to do all this, guys, so we could work a problem. Like, so suppose you go back to the think about the spring, right? All right, and then we're gonna hit it with a hammer. Let's say J naught Dirac Delta t minus. Let's say we hit it at time pi, just to be specific, right? And let's suppose that x of 0 is equal to 1 and x prime of 0 is equal to 2, all right? And I'm just, to keep it simple, I'll let it be frictionless, but we don't, I mean, that's not necessary. So what we're looking at is m x double dot, right, equals to minus kx plus the spring force, the hammer force, f of t. To make our life easy, let me suggest that we choose m and k equal to 1. All right. It's been a long day. I can tolerate that much. And you can make them be whatever you want. And we could throw in friction. It wouldn't change it much. Right? So, I just wanted to show you guys how Laplace transforms work here. So this gives us x double dot, which is second derivative, right? Plus x is equal to j naught delta t minus pi. So you take the Laplace transform of both sides. By the way, Laplace transforms don't have trouble with Dirac Delta functions. That's one of the nice things. It's like the technique of Laplace transforms dovetails nicely with Dirac Delta functions. It's not a... You don't need some kind of special add-on or patch or something, you know. See here, so you get s squared x minus s x prime of 0 minus x of 0, if I recall correctly, and then plus big X equals to the Laplace transform of this, which by the way is just j naught e to the minus pi s. Does that seem right, guys? We subtract s times the initial velocity, minus the initial position. Is that how that went? The transform of a differential equation. See, here it
I think
is.
that's right.
The Laplace transform of f prime prime of s squared
Right.
Laplace transform minus s times f of 0 minus f prime of 0. Oops, I put the s on the wrong thing. S is supposed to go on that one. Okay.
Oh, no.
Yeah. Of course, you can derive that without too much work, but I'll. All right. So then you do algebra, right? So what we do is we got s squared plus 1 times x. Now I chose these both. I chose that to be 1 and that to be 2. So we have s plus 2 plus j naught e to the minus pi s. Right. And now to actually solve for the take x, it's not hard, right? We get x is equal to s plus 2 over s squared plus 1 plus j naught e to the minus pi s over s squared plus 1. And then to finish it, we have to take the inverse Laplace transform to get back to the time domain, right? So the inverse Laplace transform gives me x of t, right? Now, let's see here.
Isn't that
The
gonna
s, yeah, the s over s squared plus 1 gives me a cosine.
be
The 2 over s squared plus 1 gives me,
sine?
2 sine, because of the 2.
Yeah.
If it was 1 over s squared plus 1, so I get cosine t plus 2 sine t. This one's relatively easy because the frequency is 1, you know. If omega is 2 or something, I'd need the 2 upstairs. I wouldn't have had a 2 sine. I would have just got like a sine 2t, blah, blah, blah. Anyway. And then this, so here my f of s, right, is like j naught over s squared plus 1. You could look at it that way. So what's the inverse Laplace transform of that? F of t is equal to j naught sine of t. So that's not what I have here, though. So what I get is, I get plus, and then I have to, I mean, that's so this right here, right, you take that, and you combine it with this thing up here, right? So I'm taking the inverse Laplace transform of the exponential e to the minus pi s times f of s, where that's f of s, right? And so what I get is I get a sine of not t, but shifted t minus pi, and then u of t minus pi. And I had a j naught out here, right? Don't forget my j naught. And there you go. That's the solution for all time, before and after it's hit by the hammer, with impulse j naught. So like the initial part in purple is the response to the initial conditions. Like initially it's at 1 and it has speed 2.
Oh, okay.
That goes on until this happens.
Okay.
And past that it vibrates in terms of some you could combine these things, and you could write it in terms of, I mean, you could write it case-wise. You could write this case-wise as something like cosine t plus 2 sine t, t less than pi, and then a cos t plus b sine t, t greater than pi if you wanted to. Just a matter of some, because you can take the t of sine minus pi and rewrite it in terms of sines and cosines and so forth of t alone. But this is the method in a nutshell. So you already know the basic method, right? You take the Laplace transform and you inverse Laplace transform. The thing is, there is a natural method for taking Laplace transforms of Dirac Delta functions and also the unit step functions. The unit step function problems are uglier because they end up like the unit step function, take the Laplace transform of that, you get like a 1 over s, and then when you divide, you get 1 over a cubic, which then means you got to do partial fractions to rip it apart. It's a pain, but But I guess we'll talk more about the delta function some other day. I think it's a good place for me to stop and then start again. So
Except
I'm
when
gonna hit it.
Nice.
Yeah, I mean the other thing to talk about direct delta functions, of course, is the application of direct delta functions to point charges. That's my or point currents, I suppose, or line currents. You know, something where you have a finite amount of charge over a geometric line or point. That means the density is infinite, and yet integrals of those density functions are finite.
Yeah.
That's a direct delta function.
Oh, okay.
So anyway, so when we talk about it again, for example, if I wanted I don't know, I'm not, the thing I'm worried about is the multipliers. There's a couple things I have to be careful about how you scale it, and I don't remember that right off the top of my head, so I'm just gonna stop here. So I'm gonna stop erasing on tape, it's stupid.